Collisions. Every collision system in the world has a lot of things in common. In particular, it typically boils down to lots and lots of intersection tests between every object in the world that might collide with every other object in the world. In principle, you have to walk through them all and test each of them and compare them all to see if they each intersect with each other. Of course, in practice, that boils down to an n-by-n intersection test, which can be prohibitively expensive. So you have to have some kind of mechanism to limit all that. And that's what the collision interface basically provides. It gives you an interface to specify the things that we divide the world into we call from objects or colliders, and into objects, which are just the collision nodes in the scene graph. And the collision system gives you a mechanism to specify which particular objects you want to consider the from objects, and everything else is just implicit in the scene graph, the into objects. The difference between the two is largely arbitrary, but by convention, the from objects or the colliders are typically the things that are moving around in the scene, the active objects. The avatars, the ships, the bullets, the grenades, whatever you want to actively think of as moving and testing collisions with things in the world. Typically, the things in the world are passive objects and not really moving that much. The collision system doesn't actually require that. It doesn't really matter that much which object is doing the moving. Basically, the collision system is going to test all of your from objects every frame with all the into objects every frame. A particular object might be either a from object or an into object, or it could be both. Usually it's not both, but it's possible. Let's see. Normally, the from objects, the colliders, are created explicitly by a programmer. A programmer will create a collision sphere that corresponds to an avatar and parent it to the avatar, so when the avatar runs around, the sphere goes with them. The into objects that the avatar might be colliding with are typically created as part of the artist's pipeline and end up in the egg piles that get loaded up. So typically, when an artist lays out a scene, they'll lay out all the polygons that make up the environment, and then they'll also lay out the collision polygons that correspond to that same environment. Many times those are the very same polygons. Ideally, though, they're typically a different set with reduced vertices, because the collision system is much more sensitive to complexity than rendering is. You can render a scene with an environment that might have many tens of thousands of polygons, but typically you only want to collide with a couple hundred at tops. So hopefully your artist can produce a collision scene which is a sharply reduced number of vertices from the actual visible scene. Let's see. In the scene graph, we end up with collision nodes, which are most of what the collision system works. They work a lot like geom nodes. Let's do a comparison. If you remember from a previous lecture, a geom node is a subclass of Panda node that is capable of holding one or more geoms, and the geom is the actual vertices that we render when we want to see what something looks like. So inside a geom node, you might see these geoms which contain the actual visible vertices. A collision node is similar in concept. A collision node contains one or more collision solids. So inside a collision node, you might find one or more collision solid. The thing about a collision node is it's not normally visible, but the reason it's not normally visible is because it's by default hidden. You can in fact show it. If you do collision node.show, suddenly you will see the collision geometry. That's only a cheap hack that happens down inside Panda, because what it's actually doing is at runtime it creates a geom and sends it to the renderer when you show the collision node. It's not meant to be shown. You can show it just as a quick hack so you can see where your collision geometry is. The pathway that renders it is not very optimal, but it's fine for just visualizing your collision solids. In fact, you can see this if you load up your game and do toggle CS or any of these funny magic words that turn on your visible geometry, your frame rate plummets. And that's not because you've got so many vertices, it's because it's doing this really long, hacky way just to visualize this thing. And that's okay, because that's not the point. Similarly, by the way, you can use a geom node as a collision node, and I'll get to that in a little bit, but it's not meant for that. And if you do a geom node and set the collision mask so that you actually collide with it, what it's going to do is the same thing in inverse. It's going to create collision geometry on the fly, which is hideously expensive. So you can do it, not meant for it. It's best to use a collision node for collisions and a geom node for reasonable stuff. Anyway, the collision node can come into the scene through loading up an egg file, and the egg loader just happens to look for certain flags in the egg file that indicate that the geometry here, the polygons in this particular part of the egg file, are meant to be interpreted as collision nodes and not as polygons. Typically, the artist will flag these with a tag in Maya. We use the barrier tag a lot, and cam barrier, and various variants on that sort of thing. I won't go into what all those mean because those vary from project to project. But the point is that those flags set in that key flag into egg that tells the egg loader that this is meant to be collision nodes. And that's how you get most of your collision nodes in the scene graph. You can also create a collision node on the fly, and this might be what you'd want to do for your avatar. So we do this a lot when we're setting up avatars. We create a collision node, then also create a collision sphere, which is a type of collision solid, and add it to the collision node. And we add it to the scene graph, compared it to the avatar, and we're all good to go. Let's see. So in the end of the day, we got a scene graph. It's got lots of stuff in it. It's got lots of collision nodes, lots of geom nodes, maybe another collision node here, more geom nodes, all these nodes, and we want to perform a collision test. Now this is what the collision traverser's job is, but as I said before, if we just told the collision traverser to ask what's intersecting, you have to ask every node against every other node, which is of course too expensive. So rather than having it do that, we designed the collision traverser so that we specifically tell it which nodes we want it to consider the active nodes, and then it will consider only those nodes against all the other ones. So when you set up a collision traverser, this is just an object that lives somewhere else. It's not part of the scene graph. You have to keep a handle of it to yourself. And you can call collision traverser.add collider. And you'll give it the node path to your collision node and a handler. I'll talk about the handlers later, but for now, the point is that you give it a collision node, and you can call any number of add colliders, and that just tells it your key collision nodes that you want to consider for collisions. Now what it's going to do is it's going to take those collision nodes and compare the from collide mask of those nodes to the into collide mask of all the other nodes. So on every node, on every collision node and also on every geom node, there is an into mask. So this is a 32-bit mask, which is just any old bit mask you like. By default, the geom nodes all have bit 20 set, and that's the only bit they have set. This will be important in a minute. The collision nodes by default have bits 0 through 19 set. These are the lower order 20 bits of the word. So if you just create a collision node and don't do anything else with it, it's got these 20 bits set. Every geom node in the graph has this bit set. You can turn these off. You can set them explicitly later. This just gets you started. One of the things that we do in the egg file with our Maya flags, for instance, cam barrier versus barrier, the difference between those two is which bits it sets by default. If we just did a barrier, I think it just sets all the bits like this. I'm not sure. But anyway, cam barrier means physically it sets the bits that mean this particular flag will be a barrier for any avatar and for the camera as well. And that's just by convention. In our own shows, we've established which bits are used for the avatars, which bits are used for the cameras, and we have a few other bits that have other purposes. You can use these bits for any purpose you like in any given show. I would advise caution with overriding bit 20, because then you're in danger of accidentally colliding with geom nodes you don't mean to collide with. And as I said before, that's really expensive. But any other bit's fair game. Keep in mind that these 20 bits are typically already turned on. Any bit higher than bit 20 is typically turned off. So you can use that to your advantage if you don't want to go through the trouble of filling in every bit on every node. Now, when the collision traverser runs, it's got its list of colliders that you gave it. And every collider, which is, by the way, a collision node, also has a from mask. So a collision node has both an into mask and a from mask. Geom nodes, by the way, only have an into mask. The only time the from mask is used is when you add a collision node to the traverser. Every other time, the into mask is what it's concerned with. And most of the time when we talk about the collision mask, we're just talking about the into mask. The into mask is so named because it's supposed to suggest this is the mask that is used when this node is being used as an into node. Normally, when we add a node to the collision traverser as a from node, we typically set its into mask to 0 so that it will never be tested for collisions as an into node. But it doesn't have to be. If you set its into mask to something else, then anything that has a from mask with any bits in common with that will intersect with it. If you set the into mask and the from mask to have some bits in common with itself, it could intersect with itself, which is bad. Because the thing's obviously going to always intersect with itself, and you always get a collision test for that. A traverser might make a special case for that. I wouldn't count on it. Typically, you want to set both of these to non-intersecting bits. OK, so at the end of the day, we've got a collision traverser. We added a bunch of colliders to it. And then when we're ready to check for collisions, we call collision traverser.traverse. And we give it the root of a scene graph. Typically, we'll start with render. It could be any subgraph. You don't have to start with render. If you just have a little subscene that you want to investigate without investigating all the other nodes, you can start with that node instead. There is one default collision traverser, which is in base.ctrav. If you create your collision traverser and assign it to base.ctrav, then showbase will automatically call a traverse for you every frame. But if you have another traverser, and you can create as many traverses as you want, then you just be responsible for calling traverse yourself whenever you need to. When you call traverse, the traverse is going to start at the node that you name and start walking down the nodes in the graph. Now it's going to try to be smart. It could visit every darn node in the scene graph. And every time it comes across a node, in principle, it could compare the collision node that it's come across with every collision node in its list. And it's going to say, take the from mask of this node with the into mask of this node and see if there's any bits in common. If there are any bits in common, then it can check the bounding volume to see if they're anywhere near each other. And if they're kind of close to each other, then it will perform the expensive intersection test to see if these nodes actually intersect at all. In principle, that's what it's doing with all the nodes in the scene graph. In fact, it tries to be a little more optimal than that. It tries to prune the graph when it figures out that there's no more reason to go any further. For instance, if there are no collision nodes in this branch of the scene graph at all, it wouldn't have to visit the scene graph at all. It doesn't have to visit this geom node or any of these geoms or anything under here. So it could look up here at this node and realize that it only needs to visit this branch and this branch. It doesn't have to visit these other branches. It really does that based on the collision mask. The into collision masks have a special property on the scene graph. They propagate upwards. So on any given node, I can call get net collide mask. And that means give me the union of my into collide mask plus the union of all the nodes below me, their collide masks. That means I can ask this node, get net collide mask, and it will compute. There happens to be no nodes below this one, so it would just be the same thing as the get collide mask on this node, which hopefully would be 0, or at least bit 20. No more than that, because there aren't any other collision nodes down here that have a different collide mask. And if I call this node get net collide mask, it's going to return the union of all of these nodes' collide masks. This value, get net collide mask, is already cached in the scene graph, the same way we cache the bounding volumes. So it's very quick to get this answer. And the collision traverser takes advantage of this to prune the scene graph so that it doesn't have to visit all these extra nodes. For instance, if it has, if it has a from node that happens to have bit 1 set, and it looks at this node and asks to get net collide mask, and the get net collide mask doesn't have bit 1 set, it's not even going to visit any further. It's not going to look at any children. But if it does have a bit 1 set, then it's going to visit the children. And then for each of those children, it's going to see, does the children have any bit 1 set. Furthermore, because it has multiple colliders, and some of these might have different bits set, it can be smart about this. If it say it has 2 colliders that have bit 1 set and another collider has bit 3 set, then it can look to see if it visits this node and sees it has bit 1 set, it'll come down here with just those 2 that have bit 1 set. And it sees that this one has bit 3 set, it'll prune out those others for its list as it visits this one. This means it needs to keep track of the current colliders at every level as it's visiting, because each time it goes down a node, it might have to remove some active colliders from this list that are no longer concerned about this node. That means it has to keep a bit mask of all the colliders that it's maintaining. That has, in the past, limited us to having just 32 colliders associated with the collision traverser at once, because there are 32 bits in the bit mask. Nowadays, we've got some code in the traverser so that if you add more than 32, it'll make a second pass over the scene graph. So it can only handle 32 colliders at once as it processes through the scene graph. If you give it 33, then it'll process the scene graph once for the first 32, and then process the whole scene graph again for the last one. And up to 63. If you give it the 64th. If you give it the 65th traverser, then you've got the 3 passes. We did experiment once with having this thing carry around a wider bit mask, say a 64-bit mask, or even a dynamic bit array. Turned out to make 0 difference. It's basically going to visit the same number of nodes the same number of times. Okay? This should give you an idea of some of the things you can do to structure the scene graph to make the intersection test more efficient. If you collect your collision nodes together that are grouped by bit mask, that helps. So all the things that are walls happen to be grouped together, and all the things that are camera mirrors happen to be grouped together. Well, that'll help a little bit, because we don't have to take we don't have to consider both nodes for both types of things. Also, the bounding volume helps. And this probably helps more because it's easier to group this way. In addition to checking the bit mask, we check the bounding volume at each place. So when we start at the top node, we first check the bounding volume of this top node, which includes all of its children, because that's the way the Panda's bounding volume works. We check the bounding volume of the top node versus the bounding volume of each of its colliders. And if the bounding volumes don't come close, it doesn't even bother. But it's the same rule. If it comes close on some of the colliders but not on others, it's going to keep just those interested colliders and carry on with the rest of the scene graph. So that means if you have collision nodes that are widely separated in space, it's good to keep them separated in the scene graph also, because that means when we visit one, we don't have to have all the other colliders in the world checking against that one. In general, we're just minimizing the number of nodes that we have to visit during the collision traverser. There's one, let's see, there are a couple ways to set the collide mask on the collision node. I mentioned that you can set them on the egg file by using the artist tags. And that way they're just set from the beginning and you're okay. You can also set them at runtime. There's a collision node interface you can call set into collide mask, and explicitly set a collide mask on a particular node. There's also a node path interface, which is a higher level function. It's a little bit easier to use. And it's just nodepath.set collide mask. It's not set into collide mask, it's nodepath.set collide mask. This is different than the Panda node set into collide mask because this is recursive. If you call nodepath.set collide mask up here, it's going to recursively visit all the nodes below you and set that same collide mask on all the collision nodes and geom nodes it defines. And that's a handy way to set a whole scene. But you have to be careful, of course. You don't want to accidentally set it on the scene that contains a lot of geometry and suddenly make your geom nodes active for collisions, because that's very expensive. Actually, nodepath.set collide mask has a bunch of options. And you can use it to set a bunch of bits recursively. You can use it to clear a bunch of bits recursively. And you can use it to basically replace the entire word or some part of the word. I think it has some options also to restrict it just to working on collision nodes and/or geom nodes. But it's a handy function to use, and it's a lot easier than going to a particular collision node and just doing a set collide mask on that.
Is that only into mask that's going to set, or will it also set the from mask?
That is only the into masks that it sets. The assumption is that from mask you only want to set on a per node basis. You wouldn't want to set it on a whole scene. Because typically you would set it just as you're adding it to the traverser. Now, let me emphasize the difference between from and into. One of the things naive users do at first is want to make every collision node that they have in the scene a from object. They want to add all the collision nodes to the traverser. But there's no requirement for collision nodes to be in the traverser in order to be intersected with. The collision traverser will visit all the nodes in the scene graph. Just putting a node in the scene graph and setting the bits properly is sufficient to make it active for collisions. If you want to have a wall or something like that you think your avatar might collide with, that's good, just put it in the scene graph. You don't need to take your wall and add it to the collision traverser. It confuses a lot of people, this idea about having to add some nodes to the traverser and not others. If you typically think about moving your active objects to the traverser, that's usually the right thing to do, although not necessarily. For instance, if you have a lot of bullets flying and they're only hitting one target, it might make more sense to have your target be the active object and all the bullets be the static objects, just because the cost of having the number of traversers, the number of colliders in the traverser. But most commonly, your active objects are few, and the static objects are many. Okay. Is everybody with me so far? Questions about bit masks and bounding volumes and collision nodes, geom nodes?
If you dynamically remove or add new collision nodes in there, what happens to the? You said it caches the mask. When does it actually update that?
Right, that's a good question. The net collide mask gets updated dynamically by Panda without you having to think about it, and it happens automatically. In fact, it happens at the same time the bounding volume gets computed. It's kind of a bounding volume in a sense. It's a bounding volume. We're showing the bounds of all the nodes below me in bitmask space, in addition to in 3D space. So it makes sense for it to be piggybacking on the bounding volume computation. And it's the same sorts of things. When I remove a node from the scene graph, that's going to propagate up the bounding volume. If I add a node to the scene graph, it's going to change the bounding volume. At the same time, we can change the collision bit masks as we're going. So the long answer is it piggybacks on the bounding volume. The short answer is whenever you call, the first call, get net collide mask, if it hasn't been computed already, it's going to recompute it on the fly. And when you remove a node and add a node, it's going to propagate upward, just the dirty flag. And then next time you check that particular node, it'll notice the dirty flag is set, and it'll recompute it then. What actually boils down to happening is, as soon as the collision traverser runs, it's going to recompute all the masks at that point if you change anything. And also, typically, the collision traverser is a bad boy who recomputes all the bounding volume for a similar reason. This, by the way, is worth pointing out. If you look at the collision traverser in pstats, sometimes you see a lot of time in the collision traverser that isn't necessarily strictly due to collision traverser time, because some of the time spent is updating bounding volumes and stuff like that. This is work that would have to be done anyway, but the collision traverser is just the first one to come along and do it. So if you take collision traverser out, it's just going to move that time into, say, render or something like that. But it's something to keep in mind when you're looking at the total time in the traverser. That's also one of the reasons that when you look at if you look at the traverser in pstats, you can see if you've gone beyond 32 colliders, you can see the number of passes. Each traverser shows up in a different pass. And you'll typically see the pass 1 is real big on the pstats graph, and pass 2 and 3 are much smaller. Part of that is because pass 1 is computing all the bounding volumes. But mainly that's because pass 1 is also pre-computing all the transform caches. Remember in a previous lecture we talked about how Panda pre-computes the transform cache. Every time you compute one node to the next and compute the transform there, that's a matrix multiply the first time you do it. Thereafter, the second time you do it, it's already been cached. So all that time is spent in the first traverser, and the second pass is much faster because all the stuff's already cached. That's one of the reasons why it's not so bad to do multiple passes with the collision traverser. Okay. Speaking of transforms, there's one minor detail about the way that we deal with transforms in the scene graph. Now, the traverser has some interesting problems because it's got this list of colliders, which might be in their own coordinate space. You know, the one object is being hurled from my, for instance, a cannonball being hurled from a boat is now in global space. But another object it might be colliding into is maybe a sail on top of another boat, which is in the space of that boat, which is in its own little coordinate space. We have to do the intersection test in some common coordinate space. The way we solve that problem is as we visit each node in the scene graph, we take the list of colliders and invert them into the coordinate space that they're going into. So if there's a scale on this node, for instance, or say there's a node above here, this one is pointed to that one. say there's a scale on this node, that means we have to invert that scale and apply it to our collision system, our collision nodes in the collider, and bring it into the same coordinate space on this one. Does that make sense? Because if there's a scale on this guy, it's making this guy seem arbitrarily big. We scale this guy up by a factor of 2, suddenly this guy's twice as big. That means we're going to bring this guy into the same coordinate space. If we just bring him in without scaling him, he'll be arbitrarily big. We have to invert the scale and make him the same size as the other guy. Of course, translation and rotation all happens invert in the same way. But because we do this, the scale of this, we apply the scale in the scene graph to the nodes in the object. This means that non-uniform scales give us problems. Because if we take a sphere, for instance, and apply a non-uniform scale to it, suddenly our sphere is not a sphere anymore. It's now some kind of crazy ellipsoid. But our collision test isn't built to handle ellipsoids. So it's going to just pick some arbitrary sphere that happens to be close to the ellipsoid scale. I think it just picks one axis and uses that scale, which usually is not right. For that reason, non-uniform scales really tune poorly if you apply it to a collision node. Best way to avoid that is, sorry, don't use non-uniform scales. You can use a uniform scale, it's okay. Sometimes that causes problems too. Translates and numbers don't cause any problems at all. But if you have to have a non-uniform scale on a collision node, it's best to flatten it out. You can call nodepath.flattenLight. That applies your non-uniform scale or any kind of transform directly onto the vertices. And that works fine as long as you're not applying it to a collision sphere, because again, you non-uniform scale a collision sphere, you flatten the scale onto it, well, what's it going to do? It's still got to be a sphere. Sorry. There's no ellipsoid collisions in the collision graph. If you have a collision sphere, if you need to have a sphere, you might want to work with a tube or maybe polygons if you absolutely have to have an ellipsoid shape. If you have a set of polygons, you can flatten any kind of scale you like on that. Not a problem.
Okay. Is there an extra cost for flattening
the flatten cost itself exists. I'm sorry, there is a cost for performing the flatten, but it's relatively small. And once it's flattened, it's actually much faster. So in general, flatten is an optimization step. You would typically load up your scene and call flatten, and there are various forms of flatten. But once it's been flattened, it's faster because now there are fewer transforms, and there is therefore less work that all the operations have to do while traversing the scene graph. Let's see. Let me re-emphasize again. One of the things that Panda makes easy is collision with geometry. But it's almost too easy because people can get in trouble this way. It's easy to accidentally collide with geometry. And geometry is real expensive because, as I said before, when the traverser is visiting the geom node and decides it has to collide with it, it actually has to generate collision polygons on the fly, dynamically generated them, performs an intersection test with it, and then throws it away. It's a terrible, terrible interface. But it's what we got, and it's much easier than doing it the right way, which would be a lot of work. Since we normally never collide with geometry anyway, and typically geometry has too many polygons to be an efficient thing for collision tests anyway, we don't really care that much, but it does mean that you have to be careful. So don't accidentally collide with geometry. Now there are times when you really do want to collide with geometry and you don't mind the cost. We do this a lot for picking from the scene graph, or for picking from the window, for instance. We have a system that when the direct tools where you just create an array that corresponds to the point of view through your window that you're pointing with your mouse. And that shoots into the scene and intersects with all the geometry in the world. And the idea is just to figure out what the heck it is you just clicked on. Okay, it takes a couple hundred milliseconds. Big deal, right? Nobody cares because you just clicked on it. You're not doing this every frame. But if you accidentally set your avatar to collide with bit 20, you will be very sad because your frame rate is going to drop.
Is that what we do with the floor flag? Dupe floor flag?
Dupe floor. Actually, no, the dupe floor is a little better than that. Because dupe floor is a special flag to the egg loader that means create both geometry and collision nodes. So it creates parallel representations of the same geometry. And this is the way to do it if you want to have efficient collisions with geometry, is you just duplicate everything up front. So dupe floor does the right thing. you end up with a collision node and a geom node. The geom node is still used only for rendering, and the collision node is used only for collisions.
But wouldn't the floor have lots of vertices?
Yeah, that's true. The floor would still have lots of vertices, although typically floors don't, so it's probably okay.
Does it actually duplicate the geometry, or does it use the same geometry as the, if you do?
Well, it duplicates it in the sense that there are two different representations of the same geometry. The representation inside a collision solid has very little in common with the representation inside a geom. It's a list of numbers that indicate where it is in space, but that's about as far as the similarity ends. And that's because the things that you want a collision polygon to do are very different than the things you want for rendering. So yeah, it doesn't share any pointers or anything like that. It actually does duplicate the vertices.
Even though that is efficient, it should not
I
be
know.
standard practice for
Yeah.
artists.
There's artists in the room.
Yeah.
Issue caveats.
It's good for prototyping.
Right.
Yeah, right. It's really handy for prototyping. There are reasons that you don't want to do that. One is that it's easy to get into the habit of just creating a bunch of geometry and deep flooring it, and then, as Red pointed out, you might have far too many polygons that way. And the other is it's good to get a good system of having separate collisions and visible geometry, because it makes it much easier to keep your collisions and your visible geometry separate, mainly for polygon count and other reasons.
Now, polygon normal facing, that affects the collisions. So when you're talking about like the picking, when you click with a mouse and it just shoots a ray, if you are clicking on something where the normal is facing the other way, it's not going to select that, right?
I'm not sure. I
You
think
do notice things like that, but.
Maybe. It comes down to whether the collision test for intersection test for ray versus polygon respects the polygon normal. Some intersection tests do, and some intersection tests don't. And I'm not 100% sure which way ray does. I could look at the code and answer you that, but I guess it really doesn't come up that much. I mean, if the normals are backwards.
Sometimes things are hard to select in the editor.
That's true, but if the normals are backwards, you're not going to be able to see it. So.
If they have a double-sided flag,
Yeah.
you can.
Yeah. Okay, that might be. It might be that the ray respects the polygon normal, and you've got the double-sided flag on. You can't click on it. That could be. It's a good guess.
Okay.
Alrighty. I mentioned a few intersection tests. So let me enumerate the different kinds of solids we have. All of these are fair game to add to a collision node. And they all start with the name collision, so I'm just going to repeat that. First common, and usually the fastest, is the collision sphere. A sphere is the fastest calculation you can ever do. It's swell. It's just a distance check. It's a Pythagorean theorem. We love it. Collision plane is less often used, but it is the base class for collision polygon. A collision plane is actually an infinite plane. And actually, a collision plane defines divides the universe into two spaces: everything in front of the plane and everything behind the plane. It's really an infinite space. It's infinitely thick. Everything behind the plane is considered solid. Everything in front of the plane is considered empty. This is different from a collision polygon, which is infinitely thin. A polygon is just that little bit in space right here, just this bit. There's stuff behind it that's empty and stuff in front of it that's empty. Collision polygon is kind of an expensive check, actually, because in order to check for something intersecting a polygon, we have to check first to see whether it intersects the plane that the polygon resides in, and then we have to check to see if the point that it intersects that plane happens to be within all the sides of the polygon. So it's fairly expensive calculation, much more expensive than a sphere. This is why we recommend using spheres whenever we can. But sometimes you just have to have a polygon, particularly walls. They're flat. You really can't do that with a sphere. So, okay, if you have to have a polygon, you have a polygon. What's that?
Whole bunch of spheres.
Yeah. You can try it. And of course, the picture gets worse when you build up a structure out of polygons. You can imagine if you've got some crazy shape, the polygons, well, we have to check each one of these. We've got to check the intersection with the planes that they're in, and then we got to check each of those edges with the point. So polygons can get pretty expensive. We also have a tube. A tube is, we probably should have called it the capsule. This is what other collision systems call it, but we call it a tube for no good reason. It's a cylinder, except that instead of just being a flat-ended cylinder, it's got hemispheres on both ends. And the main reason we put the hemispheres on the end is just because it makes the collision calculation so much cheaper. Flats are really hard to intersect with. It can be arbitrarily wide and arbitrarily big, but typically you use a tube whenever you have something that's vaguely cylindrical. It can be vertical, of course, it can be horizontal, it can be any kind of angle you like. We also have ray, segment, and line. These are almost never used in the scene graph. These are typically used for picking things out of the scene graph. And they're pretty much the same, variants on the same thing. A line is infinite in both directions. A ray is infinite in only one direction, and a segment is finite in both directions.
We do use them for shadow placement, though, and gravity.
Right. We typically, for figuring out where the ground is underneath an avatar, we'll have a ray sitting somewhere at the avatar's level, maybe at his head, maybe at his feet, somewhere down there, shooting straight down. And we ask that ray, what did you collide with? And what's the first thing you collided with? And that's wherever the ground is. So we use that for placing the shadow on the ground. We use that for letting the avatar fall to the ground sometimes. And a few other purposes like that. We also use a ray for picking things out of the scene graph, as I mentioned before.
Something to keep in mind with the tube is that it doesn't seem to like to be wider than it is tall. It kind of turns into a sphere.
I'm not sure what you mean.
I've seen it happen in numerous occasions where if the radius is
you
wider.
mean a vertical tube, you mean?
Yeah,
so,
yeah, vertical tube.
Right, so if we have a very wide and narrow tube that looks
Yeah.
like this.
Right.
Well-
It kind of just squishes and turns into a sphere. It's really weird.
That's interesting. That might be a bug. But this is practically a sphere anyway, right?
Right, yeah.
Eh. Okay. Let's see. That's pretty much it for the most common ones. There's a few more exotic ones. There is an inverse sphere. Inverse sphere might be used to put something in a spherical room. It's almost never used, but there are a few special cases where you could use it. An inverse sphere is, whereas a sphere is solid on the inside and empty everything outside, inverse sphere is solid on the outside and empty on the inside. So an inverse sphere is infinitely solid, with just a little bubble of space in the middle. Obviously, if you put this in the world and ask things to collide with it, suddenly everything would be constrained to be within that sphere.
Cool.
Yeah.
Do we use that anywhere?
We actually use this in Toontown. There's a scene in Toontown in the Cash Pack bottle where you have the magnets on cranes and there are these cables that swing around. We actually implemented a hinge using an inverse sphere. It's worth drawing a picture of because it's kind of cool. So picture an inverse sphere like this. So just one bubble of space in an infinitely thick world. And inside this, we've got a smaller regular sphere. This sphere can free to just roll around inside this inverse sphere. But it can't get out because this is infinitely solid. Now, picture another one. And another one down here rolling around. Okay? Now we apparent this inverse sphere to this node. Right?
The universe explodes.
Yeah. We can actually do this again. So, this bubble of space is fixed to this guy. So this guy's just rolling around freely, and he's carrying this bubble around with him. This guy is rolling around freely inside him, and he's carrying this bubble with him. So this guy ends up just swiveling all over the place, right? Now this top bubble is attached to the end of your crane, and this bottom bubble is your magnet. And this is how the cable in the CashBot headquarters works. Now, this isn't what it looks like. When you look at it, you just see this slender cable that's swinging around. We just draw a cheap little cable. We use these as vertex points for a NURBS curve, and we make the cable follow a NURBS curve. But really, this is what's happening. You've got this crazy hinge involved with inverse spheres.
Neat.
Yeah.
Gotta have that in pirates.
Exactly, come on.
So
Wait,
no
solutions.
That's how you get on, that's how you get on the ship.
Yeah. There's a few other uses for some of the other more exotic ones. In the same scene in Toontown, we use the collision plane to build up that room. The room is an octagonal room if you look from the top. And at first we had the walls of that room modeled out of collision polygons, as we typically model rooms out of. But you know, with collisions, there's no perfect collision system, and Pandas is really far from perfect. So occasionally, things slip through cracks, and that's kind of lame. Particularly when you've only got 8 safes in the room, or however many you've got, and one of them falls through the crack and is gone. Boy, you're sad. So we changed this. Instead of using polygons, it actually creates 8 planes, and a 9th plane for the floor. And remember, a plane divides this universe into infinitely thick and infinitely empty.
Really
So-
solid walls now.
Yeah, these are now incredibly solid walls, and there's actually no chance that anything's going to slip through. So, hooray, all of our safes are safe. So, there are times when you want to use a plane for purposes like this. You can build up a nice space out of a bunch of collision planes, and absolutely nothing can get out. And that's sometimes what you really want to do. Most of the time, though, polygons are sufficient. Also, worth pointing out that planes are cheaper. Planes use fewer tests because we just do one plane test, which is actually a pretty fast test. A polygon is a plane test plus a bunch of vertex tests.
So I have a box primitive.
There's not a box, but you can build a box out of 6 planes. Yes?
I have a dumb question. So why don't we just use planes everywhere?
Well, because there's a problem if, suppose there's a doorway out of here. Oh, I can't get through that
It's
door.
only for rooms that you don't need people to be able to get out of.
Right. In the scene in Toontown, we enter the room via cutscene, we exit the room via cutscene, so it's not an issue. Okay. So in order of preference, spheres are the most preferred solids because they're really fast. Tubes are not too bad. Tubes are a good second. Planes are also a good choice if you can use them, but they're pretty rare that you can. And then we come down to polygons as the last choice for most everything else. And of course, the world being what it is, of course you have to use polygons almost all the time. These guys, you can't put in the world and intersect with them. Nothing can intersect with these guys because we don't have that kind of collision test. But you use them for picking things out of the world. Okay. And let me also, while I'm here, talk about the kinds of collision tests we have. In principle, we could have any of these could serve as either from or into objects if we just wrote all the appropriate math tests. We haven't written that many. We've written collision sphere. We've written the whole suite of things for sphere. We've got sphere into everything else, basically. That would be sphere into sphere, sphere into plane, sphere into polygon, sphere into tube, and sphere into inverse sphere. That's all the things we got. So this means if you have a sphere as your collider list, and you have one of these things in the world, it will do the collision test and come up with an accurate answer. Or, well, maybe it won't be accurate. It'll come up with an answer. We also have ray and line and segment into most of these, the same list, pretty much. That's all. Is that right? Is there anything else we got? I think that's all. Oh, we got there's another type I didn't mention, the parabola. We just invented this for pirates for our cannonballs, and I'll talk about that. But the parabola is just a special case. It's kind of like a ray, except, well, it follows a parabola shape. And we needed this, we decided, because the cannonball collisions were just not cutting it with a series of line segments. And there are some reasons that this makes a lot of particular sense. We implemented a few parabola tests. I think parabola has basically this set, same set. But we don't have, for instance, sphere. We don't have tube into sphere. We don't have tube into tube. We don't have tube into anything. So that means you can't have a tube as your active from object. You can't have a polygon as your active from object. Because we don't have polygon and stuff. Now we could. We could, in principle, we could go and write a bunch of intersection tests. We could write polygon to polygon intersection tests. We could write polygon to sphere. And then you could add polygons as your active objects. Yeah, that would be expensive. It probably wouldn't be worth it. So generally we find the spheres work pretty well as the avatar object. It's kind of a bummer sometimes. People sometimes ask for tube into things, and yeah, I can see that. And maybe one day we'll actually write tube into things, so we can have avatar bubbles be tubes instead of just spheres. Now, I think you might be asking me about tubes around the avatars.
What happens when a ship runs into an island or something? Because neither of those are spheres, right?
With the ships, we were sad about not having tubes for the ships. So the ships are actually all sorts of crazy combinations of spheres. There's a sphere here and a sphere here, and there might be a sphere in the middle. Anybody know about this?
That's about right.
It's like that.
Yeah. But it's worth pointing out, you can do this. You can create a collision node that consists of multiple solids, and that works. It's not optimal, and it kind of gets crazy when this thing, what happens when two ships collide and you have bubbles here and bubbles there. How many collision tests are you getting back? I don't know.
Air penetration too, where the ships are cross-segmented sometimes.
Yeah. If you have a ship that ends up in this guy's space, boy, are you sad. So it's not great. If we had one big tube, it would have been better. We did experiment once. One of the former employees who was working on the collision system tried to create an actual ship-type collision shape. He was doing some good progress, I think, and the code's still there and not turned on. I'm not sure if we'll ever turn it on.
He left before turning it on.
Yeah.
Like, screw it, doesn't work.
It's obviously, this would be a fairly complicated math to do, and yeah. Anyway, spheres. We pilot spheres. Yes.
Inverse spheres, are their bounding bounds infinite, or are they a weird?
The bounding volume's infinite.
Okay. So inverse spheres are actually pretty costly then overall.
Well, yeah, if you have an inverse sphere in the inverse, you'd hopefully set your collide mask on that sphere so it only intersects with a very small number of things. Otherwise, it's going to pull the whole universe inside its sphere. Okay. So far, so good? We're coming close to the end, which is good because we're running out of time. Okay, let me talk about fluid movement.
Fluids.
Normally, the collision system works just by taking a snapshot of what the universe is at the time you call traverse. And that, doesn't always work for things that are moving rapidly. So if you've got a wall right here, and you have a collision sphere that's moving this way, your active mover, suppose one frame is here, one frame is here, and the next frame is here. Well, if the collision system samples it at this frame or this frame, he's never going to know that this guy just went through the wall. Because as far as he's concerned, he's not intersecting the wall here, and he's not intersecting the wall here, and that's kind of lame. So to solve this problem, we added the concept of fluid motion. And this works by keeping track of what we call the previous transform on every node. So on any node path, you can call get transform. And that returns a transform indication, the current position, scale, rotation of that particular node. You can also call get prev transform. And this returns the transform as of the previous frame, which is, well, it's not strictly what it is, because sometimes you reset the previous transform in the middle of a frame. But in principle, that's what it generally is. The prev transform is the cast transform from the previous frame. And once a frame, we copy the current transform onto the prev transform when we reset the frame for the next frame. Now, of course, the overall position of this node is determined by its get net transform, which is the accumulation of all the transforms from its root. You have that same dichotomy, get net transform, and also get net prev transform. So the get net prev transform is a concatenation of all the prev transforms all the way up to the root. So basically for a particular node, the get net prev transform is where it was in world space last frame, and the get net transform is where it is in world space this frame. So with this information, we have enough to solve this problem. The collision traverser can look at this node and see its get net transform and its get net prev transform, which is here, and and it's going to basically compute a ray from point A to point B and see that that ray intersects this polygon. And therefore, it's going to call this polygon, this sphere, as having intersected this polygon in this frame. And it's going to do whatever it needs to do, put it back there or something like that. Now, because we kind of bolted on the Fourier transform after the fact, Panda had already been an established system for a long time by the time we came up with this idea. We didn't just arbitrarily turn it on in the collision system. Because the reason being that you have to be careful when you're updating your previous transform that you have a sensible value there. If every time you did a set pause, it left the previous transform where it was, then you might accidentally get stuck by walls even though you really want to teleport to another place. So for instance, suppose you had some effect where your avatar teleports into the scene. And his previous transform happened to be at 0, 0, 0, and you want to suddenly put him wherever he belongs in the scene, which is, 10,000, 10,000, 2,000, something like that. Something way in the middle, far away from where it used to be. If you don't carefully set the previous transform to the same value, it's going to look like he just tried to move there in the space of one frame. He's going to see, so to the collision system, it's going to look like the avatar came from this crazy distance way the heck over here, and you tried to put him right here. And that's, of course, not what you really wanted to do. You wanted him to teleport to the space and never mind any of the collisions around him. But if we aren't careful about this, you might accidentally have this strange motion, and then the collision system will say, whoa, you can't go there because there are walls in the way, and then put him outside of the room or wherever you're trying to put him. So for that reason, and for other similar reasons, we make it explicit in the scene graph. We have two different methods. Set pause is what we use for teleporting an object to a space. Set pause updates both the transform and the previous transform. We also have set fluid pause, which updates only the transform. So the effect is that set fluid pause leaves the previous transform where it was. So set fluid pause, if you do a series of set fluid pauses, it seems to be moving fluidly. Whereas set pause is a teleport operation and resets the fluid pause so that it has no previous position. This extends to all the lerp intervals. They have a fluid equals 1. If you pass fluid equals 1 to your lerp interval, it'll basically do a set fluid pause each time. So you have your lerp that moves fluidly. Normally, we don't have collisions and lerping going on at the same time, but there are cases that we do. For instance, the cannonball is a classic case. So it's important to set the fluid pause properly in that one. And also, one more thing. You have to tell your collision traverser that you intend it to make this prev transform a distinction. By default, it doesn't, assuming that you don't know anything about it. If you don't know anything about the prev transform, you don't have to think about it. You're not going to get this motion vector difference. But if you do know about it and you're willing to do the difference between set pause and set fluid pause, then you tell your collision traverser you know what you're doing by ctrab.set respect prev transform. I'm not going to write all that. Set respect prev transform tells your collision traverser that you're going to respect the previous transform, and it's going to do the calculation. Now it's worth pointing out, set fluid pause isn't any more expensive than doing a set pause. In fact, if anything, it's a little bit cheaper because it only has to update one transform instead of two. But when you do a lot of set fluid pauses, it can actually end up being a little more expensive on the traverser because when the collision traverser does this intersection test, with a previous transform in effect, it has to do more work because it's looking at this vector here. And also, it's going to have to expand the bounding volume to include both the previous position and the current position. Remember, the bounding volume of a node is typically the sphere that encloses that node. If the node is moving, the collision traverser is automatically going to expand the bounding volume to be the smallest sphere that includes both positions. And if the thing is moving very fast, that can be a very large sphere.
Or if your computer slows down.
Yes.
That's
right. If you have a chug, where suddenly there's a couple hundred milliseconds that go by in a frame, then this thing, which was moving relatively slowly, is suddenly moving very far between these two frames, and now you got this enormous sphere around it. And this was a problem in Pirates. This was one of the reasons we came up with a parabola, because as our cannonballs were moving through space, each of them was moving, nice and sedately along a parabola shape, and there's a series of line segments. We had the fluid traversal calculation on these, so every time the collision traverser would run, it would look at the previous position and the current position and draw a sphere around those, and use this sphere to decide which ships it's aiming at. This works great, but every once in a while there might be a chug. for whatever reason, some loading chug, I don't know, maybe there was some virtual memory swapping. For some reason, one frame took a little bit longer than the rest. And so suddenly from here to here, instead of going from here to here, we're going from here to here in the space of one frame. And now we've got this great big sphere. And now this sphere suddenly encloses a lot of ships that it wouldn't have been near otherwise. And because this cannibal now has to check with all these other ships that it wasn't testing with otherwise, it's going to make that frame take a long time, right? Because it's doing a lot of calculations now that it wasn't doing. And so all these other cannonballs start taking a long time. And so suddenly all these cannonballs are going real far in the space of one frame. And the whole world just drops to its knees. That was bad. So this is an example of when collisions can go wrong. We solved that problem by creating the explicit collision parabola object, which is just event ray. And the collision parabola knows what its bounding volume is. So even if it hasn't done any checks between here and here, it's not going to expand its bounding volume ridiculously large. And that seems to solve the problem pretty well.
Another side tricky thing, if you're like, man, I really like collision rays, I'm going to use a lot of them, their bounding sphere is infinite, so once you throw them on like a traverser or anything, you're basically doing bounding checks with everything in the scene. Now it's going to hierarchically do that, but it's still kind of worrisome.
Yeah, so, well, it's not quite that bad, because collision ray, it does have an infinite bounding volume, but their bounding volume is actually the infinite line that contains it. But if you put a bounding sphere around that, that is going to be an infinite bounding sphere. So what happens is, it means any node that has a bounding line is going to have an infinite bounding sphere around it, and all the nodes above that will have an infinite bounding sphere.
So don't put it in a scene graph.
Yeah.
That makes sense.
Okay. That's most of what I wanted to talk about. Let me point out just a couple of handy things that you can use to debug what's going wrong if your collisions aren't working. Let's see. First thing you can do, I would say, of course, you can do your show collisions. That's the easiest thing to do. You can use a magic word, show collisions, or if you don't have magic words for whatever reason, you can do traverser.show collisions. You got a traverser and you call it show collisions and you give it the root of the scene graph, typically render. Render is just telling it where it's going to put the geometry that it's going to use to represent the collision. So it doesn't really have to do anything to do with the node that you're traversing for collisions. It's just render because that's what you're looking at. And what this does is it turns on visualization. Anytime a collision test is detected, it's going to draw that polygon, that collision solid that you just intersected with. If a bounding volume is checked on a collision, the very lowest bounding volume before actually performing the test, it's going to draw that same node in yellow. So you can use this, you turn it on with your avatar, and as you're walking around the scene, you can see things turn yellow as you come close to them, and as you bump into them, they turn white. It's pretty handy. It also draws the normals and the points of intersection that it defines. So if you do show collisions or render, and you see everything lighting up, well, something just went wrong, right? Also, don't forget your other traversers. A lot of times you have multiple traversers. You got to do show collisions on all of them if your collisions seem to be taking too long. Another handy thing, of course, is p-stats. Your collisions show up in the p-stats graph. If you have multiple traversers, if you give each one a different name, it'll show up in the p-stats graph by that name. It's kind of handy to see where your collision time is being spent. And finally, if you're really in the dark as to why a collision is not working or why it's taking too long, you can turn on your notify. Notify, what is it? Notify level collide. Put notify level collide debug in your config.rc, your config PRC file, and it'll turn on.
Be prepared for a lot of spam.
Yeah, be prepared for spam, especially if you put notify level collide spam. Boy, that's noisy. If you put this level of notify output, it's going to tell you every single node it visits during the traverser. Because that's so spammy, it's almost intolerable. You really can't get it around in that world. So what I like to do is do this at runtime, which you can do. Don't put it in your config file, but at runtime, you get a handle to your notify pointer, which is notify.pointer. Notify.pointer. get category. This is a terrible interface, but this is what we got. Quote quote dot collide. So notify dot pointer dot get category collide. This is a pointer to this collision object, and you can do on that set severity.
You need a bigger whiteboard.
Yeah, I do. NS spam. Oh, I just got no space. Okay. So, notify severity spams is the full spamage. So you just type this in the Python prompt, and then you can just do ctrav.traverse. And it'll just traverse it on the fly, and you'll see all the results of your traversal. And then, before you push Control D to go on, you better do this again, and this time do NSInfo. NSInfo is the default collision output, and it turns off your spam. If you forget to turn off your spamage, of course, you're going to be sad. You won't be able to control. But I do this a lot for doing real hardcore debugging into the collision system. Okay? All right, how are we doing? So?
Not so.
All right, thanks, guys.